One of the most common tests that psychologists use is a chi-square test about factors. Returning to our discussion of marginal and conditional values in a table, it's asking whether the groupings are independent. This arises commonly in R in a crosstab of factors. Here's an example from the BRFSS sample that we've been using, looking at numbers of people who report they exercised in the past month and their report of general health. If you look at the numbers, a few things are evident. More people report they exercise. That's true for every health category except for poor. Now you can question the accuracy of these self-reports, along with noting that somebody would only have to do one exercise in the past 30 days to report yes, so it's not a real stringent standard. Similarly, self-reported health status is complicated since people might answer that in different ways. How would you answer that? And note there's not a simple causal relationship there. People who exercise more ought to be in better health, but people who are in poor health might have limits on their ability to exercise. Anyway, we want a statistical test that will help us figure out what amount of variation is just random versus what amount of variation indicates there's a real link between those categories. This is the chi-square test. Well, for large samples anyway. For small samples, it would be an F test. Note on what not to do. It is useful for general understanding to get conditional proportions. For example, this is conditional on each row, showing what fraction of each row reported exercise or not. Among those in excellent health, it was 88-12 split in favor of exercise. Among those in poor health, 40-60. So it's clearly a difference, a really big difference. But we do not do the chi-square test on these proportions or any other proportions, just the total number of observations. Why is that? Well, because we want independence. Here in this table, if the first row moved from 88% in excellent health who exercised down to 87, then that would automatically, just by math, mean that the 12% has to become 13%. So those two proportions are not independent. Whereas the number of people in that box, excellent health and exercise, can be thought of as independent. Like I increased the size of the sample by one more person and they could have ended up in that box of the table. So we use the actual number of people in each category for the test. And let me fend off any approaching worries, there is indeed a simple canned R procedure that will do all this. I'm going through the details though, so you can understand what that canned procedure actually does. You can get quite a ways just believing in magic. There's some procedure that generates, as if by magic, a p-value, and if that p-value is below 5%, then presto, you've got a significant difference. But as Stevie Wonder sang, and I'm not going to sing it because I don't hate you that much, if you believe in things that you can't understand, you will suffer. Superstition ain't the way. So I want you to understand a little bit of what this test is doing. To get some of the understanding, let's revert back to the proportions. Even though I told you that's not the basis of the test, it's part of the understanding of how the test is put together. Suppose these two categorizations were independent. Then the proportion of people who answered excellent health and exercise would be the 16% who answered excellent health times the 76% who answered yes, they exercise, and so forth for each box in the table. Then multiply by the total number of people in the sample to get the hypothesized under the null hypothesis number who would be expected in each box if the two numbers were really independent. That's this table, where I put these numbers in red to remind you they're not actual observations. These are the counterfactuals, what would be expected if the categorizations were independent. And note I'm rounding. These are actually not whole numbers, which hopefully reminds these are some area ideals. These are not the actual anythings. So the chi-square test depends on the difference of the actual numbers in each category from those counterfactual numbers squared. We have to square because otherwise the differences, plus or minus, would just cancel out, which is kind of usually why we square things. That gets us to the chi-square test. If the underlying data are distributed normal, then the square of normal variance has chi-squared distribution. That Greek letter chi confuses people, but the statistician who first introduced it, he didn't actually use an abbreviation for some word or anything. He just basically wanted a curly X. The key point of the name is the squared of the chi-squared test, because the distribution comes from squaring a normal variable. In R, the syntax is incredibly simple, just chi-sq test, then the two-factor variables, and the machine does all the work. It delivers a p-value. In this case, a really, really small p-value, since those categorizations are not at all independent. If you have a small sample, you'd use an f-test instead of chi-squared. Analogously to using t-stat instead of a normal in tests of the sample mean, the f-test instead of chi-squared takes account of the small sample. I'll remind one of the weaknesses of the chi-square test is it has no information about how these differ from independence. It just delivers a p-value. Small p-value tells us it's not likely these categorizations are independent. But it leaves it up to us to provide more detail about how they're related. A low p-value can tell us there's something there, but it doesn't tell us much of anything about what exactly. A final note, you might wonder if the fineness of the categorization can make a difference in the results of the test. Like in a different data set showing class grades for two groups of students, would it make a difference if the grade was recorded pass or fail, or A, B, C, D, F, or A plus, A minus, B plus, all those? Theoretically, it would not make a difference. But in actual practice, sometimes it can. This should worry you, therefore, if you read a paper that gives some kind of oddball categories. You might think they're doing something shady.